everyone. So we're going to continue on with chapter 6, and remember we're doing 6 and 7 together. But we're going to keep going on. We started or left off last time with the 3 phenomena. That's where I want to start off this time because I want to go through each of those 3 phenomena really well before we move on. So, in terms of energy, or in terms of light, we said that light can act like a wave. And we have lots of evidence, lots of experimentation that has shown us that light can act like a wave. But we also have 3 particular experiments, or 3 particular phenomena that have shown us maybe that light can act like a particle instead of so much like a wave. So we have black body radiation is one. The next one we'll talk about is a photoelectric effect. And then the third one we'll talk about is the emission of light from excited gases. Okay, so this is talking about black body radiation. And black body radiation really comes from that heated solids can emit radiation. So classical scientists long time ago, they thought that a solid could emit all of this radiation, and ultimately, if it gained enough energy, it should be able to emit all of that energy if it was like a perfect black body. So let's kind of define maybe what a black body is. We have defined a black body as something that can emit, or something that can absorb all energy. So black body radiation, or a black body, would be something that can absorb all energy. So it's capable of absorbing anything that falls upon it. Nothing, of course, on Earth is a perfect black body. There are a few examples, though, that we can use. Graphite is a pretty good example of something that could be close to a black body, but of course it's not. Black body would be something that's more theoretical. It's an ideal. We would love to see it, but we don't have anything here on Earth that actually can exhibit that exact property. So black body, just meaning that any energy that falls on it, it's capable of absorbing any type of electromagnetic radiation, and it will absorb it all. So if it absorbs all of this energy, then it could emit all of this energy possibly. And if it's absorbing all of this energy, then ultimately, classical physicists, or classical chemists maybe, thought that a black body could contain like an infinite amount of power then, or an infinite amount of energy. Because if a black body just absorbs and absorbs and absorbs, and if light is acting like waves, because we know then that all of those waves would be entering in, or that light would be entering into that black body, that it should just keep gaining more and more and more energy, ultimately then giving it kind of infinite power. It's like the infinite radiator. But there's a problem. So I want us, and I didn't include this, guys, in your PowerPoint, so I'm sorry about that, but I will post the web page for this picture here because I think it does a pretty good job. In terms of black body radiation, we assumed, so I have wavelength of radiation in nanometers. So I have, if I'm moving from this way towards this visible region here, these moving this way, my wavelength would be getting shorter as I'm moving across this way on the x-axis. Ultimately, classical scientists thought that as the wavelength gets smaller, if the wavelength is getting shorter, we know then that that shorter wavelength would have a higher frequency, and if something has a higher frequency, then in turn it's going to have a higher energy. It's going to have a lot more energy. And if that was true, then as I move across that spectrum, as I go from like radio waves to infrared waves to visible to ultraviolet to x-rays, gamma rays, then I'm going to see this huge spike in radiation. It could emit so much radiation because it's taking in, it's absorbing everything. So this is maybe what classical physicists thought, or classical chemists thought. We thought that As the wavelength would get smaller, energy gets bigger, so I'm absorbing more energy. So ultimately I would have like this infinite amount of energy that a black body could radiate. But we observed something different. We actually observed something quite different. What we actually observe is that as we start to have a smaller wavelength, we do see that we have a really large amount of radiation that maybe is kind of spiking here at the visible light spectrum. But ultimately, does it keep going? Could a black body continue then to absorb energy or radiate that energy? It cannot. So we kind of have this peak at the visible spectrum, and then after that it just falls off. So why? Classical physicists couldn't figure this out based on the idea that light was acting like waves. So it wasn't until Planck came along to figure out that ultimately when I have a really, really, really high frequency, I'm really not getting any energy. And Planck thought that possibly the reason for this was that we have kind of a finite number of frequencies that we could, or of energy that we can absorb. We can only hold a certain amount, and then after that there's like a threshold. And the graph here kind of represents that visible light region being that threshold. And we called this, or classical physicists called this, the ultraviolet catastrophe. And they called it the ultraviolet catastrophe because after the visible spectrum we get to shorter wavelengths, which would be the UV region, ultraviolet region. And we would think that the ultraviolet region, since it has shorter wavelengths, would have an even larger amount of energy that it could absorb, but we actually see the opposite. So scientists tried to use this wave model of light to try to explain this, but they couldn't. So it wasn't until Planck came along, and Planck says that we have to assume that energy is going to come in little discrete packets. It's in specific packets, meaning that I can only have a certain amount of energy that I can absorb at a time, or emit at a time. And those packets are going to be in multiples. He calls these packets of energy quanta, and that would be the plural version. So again, singular version would just be quantum. Planck proposes that the energy that a quantum can hold, or a specific amount of energy, is equal to, or is proportional to, frequency. So E equals h times V. The energy of a quantum is equal to h, which we said last time was Planck's constant, and that number is 6.626 times 10 to the negative 34th joule seconds. And this number will always be given to you, so you don't have to memorize that. I wouldn't worry about that one. But just know that if you see h here and we're talking about quanta, then I'm going to use that Planck's constant, 6.626 times 10 to the negative 34th joule seconds. And then our V here, remember, represents frequency. So E equals h times V. And Planck thought that if we have these specific amount of packets of energy, or he called them quanta, then matter can only emit or absorb energy in whole number multiples of this. So what do we mean by that? I could have then energy equal to HV, or I could have energy equal to 2 times HV, so double that. Or I could have the quantum be equal to 3 times HV, or 4 times HV, or 5 times HV, etc., etc., etc. So this quantum is a fixed amount of energy. It's a discrete amount. So please write that down. We know it's a certain amount. It's a calculated amount. It is fixed. And that could be emitted or it could be absorbed. So it's always going to be in these whole number multiples of our HV. Okay, so if let's say we had energy that was 3 times HV, I would say then that we would have 3 quanta of energy that was absorbed or emitted. Or let's say I have 4 HV, I would say there was 4 quanta of energy emitted or absorbed. Because energy can be released only in specific amounts. We say that allowed energies are quantized, and quantized just meaning that quanta means a specific amount of energy. So if energy is being emitted or absorbed, we know it has to be in a specific amount, so we just say that that energy is quantized. And Planck actually won the Nobel Prize for working on this particular work with quantized energies in physics for this. But I know we're talking about it in chemistry, but it has a really big effect also for us in chemistry. Okay, so an analogy for Planck in terms of these quantized energies. Let's say that we're thinking about a person walking up a ramp versus walking up steps. So the person walking up a ramp, the potential energy of this person would be increasing in a uniform, continuous manner. So he's just moving up the ramp. I can say then that potential energy would be just increasing continuously because it's just a uniform kind of path here. And we know that the potential energy would increase because that height would be increasing, so potential energy in turn would also increase. But let's think about a person walking up or moving up a set of stairs or a staircase. In this case, potential energy of the person walking up the stairs is also increasing, but in a quantized manner, meaning I have to have a certain amount of energy to move from this step to this step. And I need to have a certain amount of energy to move from this step to this step, and this step to this step. So because I have to have a specific amount of energy to make sure that I don't fall down the stairs or trip up the stairs, then the amount of energy has to be specific. So it's kind of the same thing as when we're talking about this quantized energy. I can only absorb a certain amount of energy or emit a certain amount of energy to have those atoms or to have those electrons move where they need to go. The reason that it's so hard for us to see this, for us to see that energy needs to be emitted or absorbed in discrete amounts or in specific amounts, is because our eyes, the energy is so small that our eyes can't detect it. So it's really, really hard for us to understand this phenomena of energy being emitted or absorbed in packets of energy or quanta, because we actually can't see it on the macroscopic version with our eyes. We can only theoretically think about it on that microscopic level. So it stinks that our eyes aren't good enough to see it, but we do have evidence that it's happening, that we have energy that's quantized. Okay, so let's calculate the energy of one quantum of electromagnetic radiation whose frequency is 5 times 10 to the negative third per second, which I could also say hertz. Can this radiation produce a burst of energy? E equals 5 times 10 to the negative 36 joules. Why or why not? So let's answer the first question first. Let's calculate the energy if I have a frequency of 5 times 10 to the negative third per second, or hertz. So I know on this problem that we know frequency is, was it 5? Yeah, 5 times 10 to the negative third hertz, or a per second. And I'm trying to find E, and I know that energy and frequency are related through Planck's idea, which was E equals h times V. Well, I know h is Planck's constant, and I know where I could find that. That would be on my constants page of my AP test. So I could find energy, and that would be Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds, and then times my frequency, which is 5 times 10 to the negative third per second. If I multiply those together, I'm going to end up getting 3 times 10 to the negative 30th joules. Okay, so we did that first part of the question. We answered, or we calculated the energy of one quantum. So now it asks, can this radiation produce a burst of energy that would be equal to 5 times 10 to the negative 36 joules? If this is one quantum, that means this is kind of, this 3 times 10 to the 30th would be my baseline. So we said that the second quantum then, or if I doubled this, would be then the next whole number ratio of emission or absorption that I could have. So 2 HV would give me then 2 times 3, 2 times this value here. I'm sorry, I can't talk today. 2 times this value here. 3 times my HV, or 3 quantum, would give me 3 times this number. If I did 4 quantum, it would give me 4 times this number. 5 quantum would give me 5 times that number. So can this amount of energy give me a burst of 5 times 10 to the negative 36th? And it cannot, because 3 times 10 to the negative 30th joules will not give me a multiple for this number. Remember that our quantum of energies can only be multiples of what we calculated here. And I calculated that the first quantum was 3 times 10 to the negative 30th. If I continue to take multiples of that, I'm not going to get 5 times 10 to the negative 36th. So because it's not a multiple of that first quantum, it will not produce a burst of this amount of energy, okay? So let's move to the second phenomena, which I think is like super cool, because I'm really weird like that, of course, which is the photoelectric effect. So Einstein was the one that worked on the photoelectric effect, and pretty much what he assumed was that I could have light coming in, and when light strikes a clean metal surface, so if light shines on a clean metal surface, it can, the metal surface can absorb all of that energy, in terms of light here. So I have light coming in, the clean metal surface is absorbing all of that energy. If that metal absorbs that energy, remember that if we're thinking about metals, the metallic bond, we have that sea of electrons. So if it's absorbing energy, then some of those electrons can become excited, and that could cause some of these electrons to be emitted from that metal. So I'm absorbing this clean metal surface is absorbing all of this energy from the light. It's exciting some of these electrons, and I can see these electrons leaving or being emitted from the metal. So in terms of Einstein's idea of light, Einstein assumed then that the energy striking the metal surface would behave more like a stream of tiny energy packets. And he said that each packet would be more like a particle of energy. So instead of acting or thinking about light acting like a wave, he thought that light would be coming in discrete packets, more like particles, instead of so much like a wave. And the metal could absorb those particles. And those particles are something that he called photons. And a photon, so we have photon here, a photon is just a particle that has no mass